It's a simple idea, really. Plants do it. They just sit in the sun, they take in some water, breathe in a little air, and make their own food. It seems so easy, so elegant. Why can't we do that? Imagine a world where you never had to pack a lunch. No more grocery shopping, no more dishes. Feeling a little low on energy? Just step outside for a few minutes. It sounds like a superpower, but we can't. Not even a little bit. And the reasons why are not small. They are fundamental to what we are. They are written into our size, our shape, our skin, and our very need to move and think. The gap between us and a plant is not a small step. It is a vast chasm carved by 500 million years of completely different ways of living. To understand why we can't photosynthesize, we have to look at what it would actually take. We have to look at the numbers, the biology, and the sheer inefficiency of it all when applied to a creature like us. First, let's get the basics straight. What is photosynthesis? At its heart, it is a chemical trick. It's a process that turns light energy into chemical energy. A plant uses a special green molecule called chlorophyll. This molecule is an expert at catching photons, which are tiny packets of light from the sun. It uses the energy from these photons to break apart water molecules and carbon dioxide molecules. Then it rearranges the pieces to build a new molecule, glucose. Glucose is a simple sugar. It is pure energy, ready to be used. As a bonus, the plant releases the leftover oxygen into the air. So, the ingredients are sunlight, water, and carbon dioxide. The factory is a tiny organelle inside the plant cell called a chloroplast, which is filled with chlorophyll. The product is sugar, and the waste is oxygen. It's the most important chemical reaction on Earth. It powers almost everything. So, to do this ourselves, we would need to have this machinery. We would need chloroplasts filled with chlorophyll inside our cells. Let's imagine for a moment that we could do this. Let's say, through some miracle of genetic engineering, we could make our cells produce chloroplasts. Where would they go? The only logical place is our skin. It's the only part of us that sees the sun. So, now we have photosynthetic skin. We are green, not a light, fashionable green. A deep, dark, leafy green. Because to catch enough sunlight, you need a lot of chlorophyll. Your skin would have the color and maybe even the texture of a spinach leaf. This is the first and most obvious change. We would all be green. But looking like the Hulk is the least of our problems. The real issues are about math. Cold, hard numbers. And the numbers do not lie. The first problem is surface area. Think about a plant. It is designed to maximize its surface area to catch light. A big oak tree is not just a trunk, it is a massive network of branches, twigs, and thousands upon thousands of leaves. If you were to take all the leaves off a mature oak tree and lay them flat, they would cover a football field. That is a huge solar panel. Now think about a human. Our skin is our solar panel. The average adult human has about 2 square meters of skin. That's about the size of a door. For a football field versus a door, the difference is staggering. A plant's whole life is about creating as much surface area as possible to soak up the sun. Our whole life is about being a compact mobile unit. Our design is completely at odds with the needs of photosynthesis. We are a terrible shape for it. We are a walking, talking bundle of inefficiency when it comes to catching light. Even with our pathetic 2 square meters of skin, let's see what we could do. Let's run the numbers. On a bright, sunny day, the amount of solar energy that hits 1 square meter of Earth is about 1,000 watts. A watt is a measure of energy per second. So with our 2 square meters of skin, we could be hit with about 2,000 watts of energy. That sounds like a lot. But photosynthesis is not very efficient. It's actually terrible at converting light to energy. Most plants, under ideal conditions, can only convert about 1 or 2% of that light energy into chemical energy. The rest is lost as heat or reflected away. So let's be generous and say our new green skin is 2% efficient. 2% of 2,000 watts is 40 watts. That's our total energy production, assuming we are lying naked on the equator at high noon. We measure our energy intake in calories, or more accurately, kilocalories. A moderately active adult needs about 2,000 to 2,500 kilocalories per day. A 40-watt output is about 34 kilocalories per hour. So if you were to lie perfectly still, naked in the sun, for a full 10-hour day, you would generate about 340 kilocalories. That is not even enough to cover your energy needs while you sleep. Your brain alone burns about 300 to 400 kilocalories a day just thinking and keeping you alive. The energy you would make from a full day of sunbathing would barely be enough to power your brain. You would still need to eat a full meal, or 3. just to break even. Photosynthesis would not be a meal. It would be a tiny, insignificant snack. It would be the equivalent of eating a single apple over the course of an entire day. It's simply not enough. The math just doesn't work. We are far too energy hungry. This brings us to the next big problem, our metabolism. We are warm-blooded animals. We burn a massive amount of energy just to keep our bodies at a steady 98.6 degrees Fahrenheit. This allows us to be active in the cold, to think fast, and to move quickly. A plant is the opposite. It is cold-blooded. Its internal temperature is the same as the air around it. It does not move. Its lifestyle is slow. It can afford to run on a trickle of energy. We cannot. Our high-energy lifestyle is what defines us as animals. We hunt, we run, we build, we think. All this requires a huge, constant supply of high-density fuel. We get that by eating plants and other animals. We are consuming concentrated energy that took months or years to accumulate. We are built for feasting, not for the slow, patient work of photosynthesis. Trying to power a human body on photosynthesis is like trying to power a jet engine with a handful of wood chips. The engine is just too powerful for such a low-grade fuel source, and the biological hurdles just keep getting bigger. Let's go back to our green skin. Our skin is not like a leaf. A leaf is thin, almost translucent. This allows sunlight to penetrate deep into the leaf and reach all the chloroplasts. Skin is thick and opaque. It is designed to do the opposite of a leaf. It is designed to block sunlight, especially harmful ultraviolet radiation. It has layers of dead cells on the surface. It has pigment like melanin. All of these things would get in the way of photosynthesis. If our chloroplasts were only in the top layer of skin, most of them would be in dead cells. They wouldn't be able to do anything. If they were in the deeper living layers, sunlight would never reach them. We would have to evolve completely new skin, something thin, fragile, and transparent. We would be incredibly vulnerable to UV radiation, cuts, and infections. Our protective barrier would be gone. Then there is the problem of plumbing. A plant has a sophisticated system for moving things around. It has xylem to pull water up from the roots and phloem to move the sugars from the leaves to the rest of the plant. It's like a system of pipes. We have a circulatory system, but it's designed to carry blood, oxygen, and nutrients from our digestive system. It's not connected to our skin in the right way. If our skin cells made sugar, how would that sugar get to our brain, our muscles, our heart? There is no direct highway from our skin to our liver. We would need a whole new network of vessels to collect all the tiny bits of sugar from every skin cell and deliver it into our bloodstream. It would be a massive re-engineering of our entire body. And what about the other ingredients? Photosynthesis needs carbon dioxide. Plants get this from the air. They have tiny little pores on the underside of their leaves called stomata. They can open and close these pores to let CO2 in. If we had stomata all over our skin, we would have a huge problem with water loss. We would be constantly dehydrating as water evaporated out of these tiny holes. It's a fine balance for plants, and they live in a world where they can usually get more water from their roots. We can't do that. We would have to drink water constantly, far more than we do now, just to keep our skin breathing system from drying us out completely. It would also make our skin a gateway for germs and pollutants. It would be another major vulnerability. So, direct genetic engineering seems impossible. We would have to change our shape, our size, our skin, our metabolism, our circulatory system, and our respiratory system. We would have to stop being human and become something else entirely. Something slow, green, and very, very fragile. But what about another way? Nature has found a workaround. It's called symbiosis. Some animals have managed to borrow the power of photosynthesis without doing it themselves. The most famous example is a little sea slug called the eastern emerald elysia. This slug eats algae, but it doesn't just digest it. It carefully sucks out the chloroplasts from the algae and incorporates them into its own digestive cells. These stolen chloroplasts continue to photosynthesize inside the slug for months. The slug provides the chloroplasts with a safe home and the raw materials they need, and the chloroplasts provide the slug with a steady supply of sugar. Well, it becomes a solar-powered animal. Could we do something like that? Could we host algae in our skin? It's a fascinating idea. We could be injected with a special kind of algae that is compatible with our bodies. The algae would live in our skin or maybe even in our blood, soaking up sunlight and producing sugar for us. We would get a constant little energy boost. We wouldn't have to become plants. We would just be carrying them around with us. But even this more plausible scenario is full of problems. The biggest one is our immune system. Our immune system is incredibly good at identifying and destroying anything that is not us. It would see these algae cells as foreign invaders and would immediately attack them. We would need to either completely suppress our immune system, which would leave us open to every disease imaginable, or find a type of algae that is somehow invisible to our immune cells. This is an enormous biological challenge. The sea slug can do it because its immune system is much simpler than ours. It has evolved over millions of years to tolerate these specific chloroplasts. We have not. Even if we could solve the immune problem, the math still doesn't get much better. The algae would still be limited by our small surface area. The energy boost would be minimal. It might be enough to feel a little less tired on a sunny day, but it would not replace food. It would be a supplement, not a solution, and we would still have the color problem. Our skin would likely take on a greenish, blotchy appearance as the algae colonized it. It might not be the most attractive look. And what happens at night or in the winter? The algae would become dormant. They might even die off, requiring us to get new injections. It would be a high maintenance relationship. There is another, more technological path. Instead of biological photosynthesis, we could try artificial photosynthesis. We could develop a kind of synthetic skin or a wearable device. Imagine a thin, flexible film that you wear on your back or your arms. This film would be a highly efficient solar panel, much more efficient than a plant. It would have tiny tubes that pull carbon dioxide from the air and moisture from your sweat. Inside the film, a chemical process powered by sunlight would convert these into a simple nutrient, like glucose or ethanol. This nutrient could then be absorbed through your skin or delivered into your bloodstream through a small port. This approach avoids many of the biological problems. We wouldn't have to change our DNA. We wouldn't have to fight our immune system. We could take the device off when we wanted to. But it creates a new set of engineering challenges. Creating a device that is efficient, durable, safe, and comfortable enough to wear all day is incredibly difficult. And again, we come back to the energy problem. Even with a much more efficient system, say 20% efficient instead of 2, our small surface area is the limiting factor. The energy produced would still be a fraction of what we need. It could be a useful survival tool, perhaps for astronauts on long missions or for soldiers in the field. It could provide a small emergency source of calories, but it would not free us from the need to eat. So we are left with a simple truth. We are animals, we are built to move and to eat. Our entire evolutionary history is a story of becoming better hunters, better gatherers, better farmers. We have outsourced our energy production, we let the plants do the hard work of capturing the sun's energy, and then we simply take it from them. Or we eat the animals that eat the plants. We are at the top of a food chain that is built on a foundation of photosynthesis. We are not designed to be the foundation. Thinking about human photosynthesis forces us to confront what we are. We are creatures of high energy and high consumption. Our big brains, our active bodies, our complex societies are all fueled by an enormous daily intake of calories. This is both our greatest strength and our greatest weakness. It allows us to do amazing things, but it also makes us completely dependent on the world around us. We cannot just stand in the sun. We must actively seek out and consume energy. And maybe that's not such a bad thing. Food is more than just fuel. It is culture, it is family, it is pleasure. We share meals. We cook for loved ones. We celebrate with feasts. The flavors and textures of food are a rich part of the human experience. If we got all our energy from the sun, we would lose all of that. Life might become more efficient, but it would also become more sterile. We would be independent, but also isolated. A life without food would be a profoundly different and perhaps a much emptier existence. The dream of photosynthesis is a dream of simplicity and self-sufficiency. It is a dream of escaping the constant, nagging need to find our next meal. But it is a dream that belongs to another kingdom of life. We chose a different path a long time ago. We chose the path of movement, of thought, of action. We chose to be eaters, not producers. And for all the trouble it causes, for all the grocery trips and the dirty dishes, it is a path that has allowed us to become who we are. We are not green, we are not still. We are warm, hungry, and restless, and that is a powerful thing to be. The sun gives us warmth and light, but for energy, we will always have to look to our plates.